All right, welcome guys. We are going to take a look at exponential functions today and the derivatives of exponential functions. We just got done talking about natural logs and their derivatives and integrals. And so the inverse of natural log is e to the x. And so we're going to jump into the next two lessons that are dealing with e to the x and other bases of a to the x and log base a to the x. Today's main focus is going to be just e to the x and the derivative of e to the x. So let's jump into it here. All right, so this is 5.4 for us. Exponential functions and differentiation. All right, so the natural exponential function. All right, this is our f of x equals e to the x. Most of the things we do in calculus is going to deal with e to the x and not another base. We will talk about those later. But our primary focus, again, is e to the x. Now, y equals e to the x if and only if x equals natural log of y. This is their relationship between the two. All right, natural log, we talked about, has a base of e. And so when we rewrite it in exponential form, it becomes this y equals e to the x. Okay, so y equals e to the x and y equals natural log of x are inverse functions. And so that inverse relationship that they have is pretty much this. If we were to go ahead and put the two together, natural log of e to the x, what happens is the natural log and the e cancel out, and you're left with just x. And our other one would be if you have e to the natural log of x, the e and the natural log again cancels out and gives you just x. They undo each other. The whole idea here is that these two functions act as inverses, and we're going to use those both to cancel out, get rid of, and rewrite, all those kind of different things. So we're going to start off by doing some stuff that we did back in Algebra 2 and pre-calc, and we're going to do some solving with exponential functions. So if you have an exponential function like so, 7 equals e to the x plus 1. Our goal here is to get that x by itself. Well, the way that we get rid of that e is we're going to natural log both sides. So we're going to natural log the 7. We're going to natural log the e to the x plus 1. And we know from what we just said with our inverse relationship that natural log and e, they cancel out. And since they cancel out, that's going to leave us with just natural log of 7 equals x plus 1. And then from there, all we have to do is go ahead and isolate that x, subtract the 1, subtract the 1. No, we can't take 7 minus 1. No, it's just going to be x equals natural log of 7 minus 1. And for our purposes, we would leave this unless it was a calculator problem. That would be a totally fine answer. And so you're going to see answers in this unit where they're going to have natural logs in them. They're going to have e's in them, all kinds of different things, just like we saw with our previous units. All right, now the reverse of this, let's say we have to solve a logarithmic equation. Now with a logarithmic equation, we've actually talked about this a little bit with the last sections. If we have natural log of 2x minus 3 equals 5, we got to get rid of that natural log somehow. And my phrase that I always like to use is just e it. Just e it. And so what we're going to do is e it. And so that's actually using e as a base and saying e to the power of natural log of 2x minus 3. What happens is that e and natural log, they cancel out. And then we're left with 2x minus 3 equals e to the 5th. With other logs, I tend to use another phrase, swoop it. Since you don't really see the e, I just e it. It's easier. So then we're going to go ahead and isolate that x. So I'm going to go ahead and add the 3 to the other side. 2x equals e to the 5th plus 3. And then divide everything by 2. And x equals e to the 5th plus 3 over 2. Now, again, totally fine answer. We're going to leave it just like that. And that's all there is to it. Let's try 2 more real quick. Okay, so we have an exponential one here. Again, with the exponential, we want to go ahead and make sure we get that e to the x by itself before we start doing any of our natural logs and everything like that. Okay, so what I'm going to do first with this one on my left is add the 6 over. Once I do that, I get 3e to the x equals 14. I can then divide by 3. And then I'm going to go ahead and natural log it. So we get x equals natural log of 14 over 3. Because we know that natural log and e, they're going to cancel out there. And then we have that one done. All right, on our right side, now we got a couple options with this. One thing that we saw with our natural logs, we have a power here. Okay, we have that power. We can actually bring that power to the front and then divide by 2. This does work, but things you have to watch out for with this. Because that squared is already up there in the equation, watch what happens when I e it. When I just e it, cancels out my natural log, and it leaves us with x minus 2 squared equals e to the 12th. Well, then from there, I would go ahead and get rid of that square by square rooting it. Well, when I square root it, you got to remember that that's going to give us plus or minus, and then the square root of e to the 12th is actually e to the 6th. Now, if I had brought that 2 down there, I wouldn't have gotten that plus or minus. And that's what you got to be careful with this, using those properties too early on. Because it started off as a squared, theoretically, I could put the negative e to the 6th in our problem, and that would have worked out for us. So I got to make sure I keep that plus or minus there. I'm going to add the 2, and so x equals 2 plus or minus e to the 6th. Okay, if you only got the plus because you brought the 2 down, technically you're half wrong, and you got to really watch out for questions like that. Now, again, this is all pre-calc, algebra 2 base. This isn't anything new for calculus. So we really shouldn't have too many issues with solving these, but it will become an issue when we get into finding those critical numbers, as we're going to see a little bit later today. All right, properties of f of x equals e to the x. This is an important one. We got to know what this graph looks like. And so our e to the x graph, again, we saw this in pre-calc. It was one of our 12 basic functions. Okay, we have a graph that kind of looks like this, going through 1 there on the y-axis. Okay, a couple of different things. One, our domain, if we look at this, our domain is negative infinity to infinity. And our range is from 0 to infinity. This is the exact opposite of what we saw with the natural log of x. And that's what one of our characteristics of inverse functions are. The domain and range, they flip-flop. So, a couple other things. These are actually very similar to our natural log function. The function is continuous, increasing, and 1 to 1, which we said means that for every 1x, there is 1 y value. Okay, and for every 1 y value, there's 1 x value. That's what makes these inverse functions functions. All right, and we also see that the graph is concave up. Okay, one other thing that we have to look at here is the end behavior with this. The end behavior does have a little bit of a different thing here. And if you notice that the limit as x goes to negative infinity of e to the x, well, it's going towards its horizontal asymptote. It has a horizontal asymptote at 0. And if you go to the right, limit as x goes to positive infinity of e to the x, that's going to actually equal infinity because it's going to keep getting bigger and bigger. We see this a lot as they talk about limits with e to the x. The reason why e to the x goes to 0, well, if you think about this, you put in that negative infinity for an exponent. When you have a negative exponent, we talked about that goes under 1. Well, if you have 1 over a really, really, really big number like e to the infinity, that's just going to actually be 0. And so that's why it goes to 0 as you go to the left, but as you go to the right, it keeps getting bigger and bigger and bigger since it's e to the infinity power. Okay, so those are characteristics. We do need to be able to do a quick sketch of these sometimes. And so here's a super ugly one. Let's see if we can find all of its transformations. Transformations we've seen with every single function, and a lot of times they're just going to give you some version of our transformations that we've seen. So what we see here with all these different pieces, we have f of x equals -3 e to the x minus 1 plus 4. Well, we know that plus 4 right here, that's going to shift it up 4. We have that vertical translation. That minus 1 is going to take it to the right 1. The 3, our 3 is going to make it do a vertical stretch. And our negative, all right, that negative is going to make it do a reflection over the x-axis. Okay, so we have all of our different pieces. We just got to do a quick sketch with this. We're not too concerned about it being perfect, but we got to know where it actually is, and that's the key here. And so if it's going up 4, instead of that horizontal asymptote being at y equals 0, we know that's going to be shifted up 4. Okay, we know that's going to the right 1. Normally, it goes through 0, 1. So if you raise that up to 0, 5, that point's actually going to be at 1, 5. But remember, there's a reflection, so it's going to reflect down here. And then if we go ahead and follow our path, it will be more of a stretched out version of this. So it's going to follow it down like so. Okay. Okay. Our vertical stretch of 3, that's going to really just stretch that out a little bit. So normally it would look like this. If we were to go ahead and put 1 in there, what's going to happen is you're actually going to get 1. So it's actually going to stretch out this way. So what I did before that was without the stretch. Now let's go ahead and put it with the stretch. Oh, that's a terrible graph. And so it's going to follow and go down a little bit steeper like that. All right, it's going to follow that vertical or that horizontal asymptote there. This is not one to write nicely for me today. There we go. That's nicer. There we have it. Okay, so there's all of our transformations with that graph, and that gives us an idea of where it's going as it goes to infinity, where it goes to negative infinity, different things that we may have to look at. Okay, so that's graphing. That again, pre-calc, algebra 2, nothing new with this. Now we're going to get into the fun stuff, the calculus. The calculus involved is derivatives today, and the greatest derivative of all. All right, it's going to be wonderful. We're going to hide it. The derivative of e to the x. The derivative of e to the x is e to the x. Isn't it wonderful? It's fantastic. This will probably be the easiest one for you to remember. The derivative of e to the x is e to the x. And I'm going to give you the proof because I know how much all of you enjoy proofs. So we're going to start off with this idea of e to the x. Well, I'm going to take the natural log of that. And since we know that inverse property says that the natural log of e to the x is just x. Now, what we're going to actually do with this is take the derivative of both sides. So I'm going to take the derivative of natural log of e to the x and the derivative of x. So I can't do it to one side without doing it to the other side. Now, on the right side, we know the derivative of x is just 1. On the left side, we just got done a whole unit on derivatives of natural log. So if I take the derivative of natural log of e to the x, we said u prime over u. Or in this case, we're going to do 1 over u, our u being that e to the x there. So 1 over e to the x times the derivative of e to the x. So I don't know what the derivative of e to the x is. So I'm going to write it as derivative of e to the x And the last piece I have to do here is I'm going to get the derivative of e to the x by itself, right? Here's what we're actually trying to prove. So the way that I'm going to get rid of it is, or get it by itself, is multiply both sides by e to the x. Once I do that, that goes away, and we get our final product of derivative of e to the x is equal to e to the x. Boom. There's your proof. So we have our derivative. Now we're going to apply it to all the things we've done with derivatives so far. So you're going to add this derivative into your toolbox of derivatives. And our first two that we're going to do, really what we find out is that because it's so easy, we use chain rule a lot. All right, chain rule, product rule, quotient rule, all those great things, we're going to end up seeing a lot with these. So our first one, y equals e to the 2x minus 1. Because this is so great, all you have to do, y prime would be e, derivative of e to something is always just e to something. So we're going to do e to the 2x minus 1. But then we have to take the derivative of the stuff. Derivative of the stuff, what is the derivative of 2x minus 1? The stuff is actually what's in that exponent there. So the derivative of that would just be 2. So our final answer for this one would just be 2e to the 2x minus 1. All right, same thing for our next one here. We're going to take the derivative of this, which is going to be y prime equals e to the negative 3x, or 3 over x. You're going to write e to the negative 3 over x. It's the same thing, but then times, we got to take the derivative of that stuff. That stuff is negative 3 over x. Well, remember, write that as negative 3x to the negative first. The derivative of that would just be 3x to the negative second. So if I were to rewrite this, this would be 3e to the negative 3 over x squared. Okay, and so that would be our final answer for that. So a lot of times it's just chain rule. The nice thing about e to a power, you're always going to get that e to the power of x somewhere in your answer. There's a lot of repetition with derivatives of e. Okay. So let's apply some stuff to this. Let's go ahead and find the tangent line to y equals e to the third natural log of x at x equals 1. Excuse me. Now, here's the catch with this. All right, and you got to be really careful because they like to go ahead and throw this into the mix every once in a while. If you take a look at this, e to the third, notice that there is no x next to the 3. Well, e to the third is just a constant, which means when you're taking the derivative, that's just going to hang out there. All right, you're not actually going to apply the derivative of e to the x in this case. So what two things do we need for a tangent line? We need a point and a slope. So our point, we know x equals 1. Our next thing we got to find the y. The way that we find the y is we plug it in. So y equals e cubed natural log of 1. We talked about natural log of 1. That is equal to 0. So our point is 1 comma 0. Super exciting there. And our slope, the way that we find our slope is the derivative. Now, again, like I just said, e to the third power is a constant. There's no x there. So we're not even going to use the derivative of e to the x. So this is actually just e to the third times the derivative of natural log of x, which is 1 over x. So our derivative is e to the third over x. And so we got to find the slope. Find the slope by plugging in that point. So our slope is e to the third over 1, which is e to the third. So now we have a point and a slope. Let's use point slope. Our tangent line will be y minus 0 equals e cubed times x minus 1. And you can simplify that however you'd like to simplify it. But that is all for that. Okay, so there's tangent line question. Let's try relative extrema. Now this one, e does have an x, so we do have to use it. But notice there is an x in front, so that means we need to do a little bit of product rule with this. All right, so we're going to find the relative extrema. Whenever we find the relative extrema, we got to start off with finding those critical numbers, which means we need to figure out where the derivative is equal to 0 or undefined. So let's take the derivative first. All right, we're going to do that product rule, first d second. So first x d second e to the x is e to the x plus second e to the x d first, which is just 1. So we're going to find the critical numbers now. All right, so we're going to set this equal to 0. We need to go ahead and solve this. Now, as for undefined, is e to the x ever undefined? No, it has a domain of negative infinity to infinity. And x isn't undefined, so we don't have any fractions. We don't have anything that's going to cause problems, so we don't have to worry about that. We do need to find the zeros, though. And the way that we find the zeros are we're going to factor out e to the x. So we take out e to the x, which leaves us with x plus 1. Well, if we set both of those factors equal to 0, and this is why we need to know what the graph of e to the x looks like, because we have a problem here. E to the x never equals 0. E to the x is always positive. And that's something you got to keep in mind whenever you're doing critical numbers with e to the x. If you can factor out e to the x, you never have to worry about that piece of it because it's never going to equal 0. Now, what we do have, though, is a critical number at x equals -1. Okay, so remember, when we get that critical number of x equals -1, now we make our table. We're going to do a table of negative infinity to -1 and -1 to infinity. All right, so when we go ahead and do that, we can go ahead and set up a column for our f prime and a column for f of x. And we're going to test the value in those with our derivative. So I'm going to pick a number between negative infinity and -1. So I'll pick -5. So we have -5 e to the -5 plus e to the -5. Well, that's going to give us a negative value. So we know it's going to decrease. Or don't write the negative there, that'd be bad. So a negative value here, that tells us it's decreasing. And then from -1 to infinity, let's go ahead and put 0 in there. That's a nice easy one. We end up getting a positive because we get 0 plus e to the 0, which is 1. That's going to tell us it's increasing. Well, if we go from decreasing to increasing, we know we have a relative minimum at x equals -1. Now, if we wanted to find that point, how do we find the point at x equals -1? We'd plug it back into our original. So f of -1 would be -1 times e to the -1, which actually gives us -1 over e. And so kind of be ready to write things like that. We're going to see situations where a multiple choice, especially, they will rewrite them as fractions and different things. So our point for our relative extrema would be a relative min at -1 comma -1 over e. Okay, and so that's our applications that we see with this. We really can see any other applications that show up with derivatives. But this is the main ones I wanted to talk about for this piece. Tomorrow, we're going to get into our next lesson, which is the antiderivative. So if you think about the derivative, then the antiderivative should be just as easy. We'll talk about that later. But continue doing your derivatives and good luck with the practice.